Battery-powered model race car moves around a racetrack as indicated in the diagram below. The car's initial position is at point A. At any time t seconds, the velocity vector v of the model race car is given by v is equal to negative sine t over 3, 2 cos t. Determine the initial velocity vector and show this on the diagram above. So what we're after there is v of 0, and of course the sine of 0 is 0, the cosine of 0 is 1, so that's 0, 2. So the initial velocity, we know the initial position is at A, the initial velocity would be in this direction, so 0, 2. Write an expression that will determine the change in displacement over the first 3 pi by 2 seconds. Now that's displacement, not distance, so we can do that by integrating the velocity, but not in modulus. In modulus gives us distance, not displacement, so that would just be 0 to 3 pi by 2. Determine the displacement vector. So now we've actually got to integrate, but this is just the general. So we're integrating negative sine t on 3 and 2 cos t dt. So we know that sine integrates to negative cos, so negative sine would go to cos, so that's going to be cos t over 3. We need to divide by the differential of the inside, so dividing by a third means the same as multiplying by 3, and integrating cos goes to sine, so that's 2 sine t, and of course we need constants of integration, which we'll call c1 and c2, but we know that the initial position is here at 3, 0. So we can say that 3, 0 is equal to 3 cos 0 plus c1 and 2 sine 0 plus c2. The cos of 0 is 1 and sine of 0 is 0, so that tells us that c1 and c2 are both 0. So our position vector r of t is going to be 3 cos t upon 3 and 2 sine t. It can be shown that the model race car's speed is at a minimum when it reaches the point B on the track, one of the sharpest points on the curve. So let's have a look at B. Okay, so B is just here. Determine the acceleration vector A when the car reaches point B, giving components correct to 0.01. So if we look back at the graph, we started here and we went this way. So this would be the first time that the y component, or j component, is maximized. In other words, sine t is 1, and therefore we would have that t is equal to pi by 2. Now, our initial velocity vector was equal to negative sine t on 3 and 2 cos t. So that means the acceleration vector would be sine differentiates to cos, so that's going to be negative cos t on 3 multiplied by the differential of the inside, so we'll just divide that by 3. And cos differentiates to negative sine, so that's negative 2 sine t. And we want A of pi by 2. So that's going to be equal to negative cos pi on 6 divided by 3 and negative 2 sine pi by 2. So let's just clear my main screen. So we just need to evaluate this one. The bottom one is obviously just negative 2, because sine of pi by 2 is 1. And we want this to 2 decimal places. So we are going to have, we need to be in radians here. Oh. So we've got cos of pi by 6 divided by 3. We know it's negative of that, so negative 0.29. So finally, we want to determine the distance correct to 2 decimal places that the model race car travels in completing 1 lap of the track. Now I'm actually going to work it out up the top here where we can actually see the diagram. So we know it's going to be an integral, and if it's distance, it's the modulus of v of t dt. Now think about our velocity vector. So the velocity vector, that's given to us here at the beginning. So with the velocity vector, we can see that the argument here is t over 3 and the argument here is t. So for this one to go all the way back to the beginning, the period of this function is actually 6 pi. Substitute 6 pi in here, 6 pi over 3 is 2 pi. So it's going to be 0 to 6 pi, not 64, 6 pi. So we've got the integral from 0 to 6 pi of the square root of sine squared t over 3 plus 4 cos squared t dt. Now I'll just pause the recording while I was typing all of that in, and it comes to, as we can see, 28.16, and it's in meters.